Welcome to EDU World Space.
Okay. In this, we have a pretty interesting problem here. We have a laser beam refracting across some surface, and the beam initially has some diameter of 3 millimeters. It enters at an incident angle of 25 degrees, and it passes from air to glass, I believe. Yeah. The air has an index of refraction of 1. The glass has an index of refraction of 1.5. And as it refracts across this surface, it'll actually increase its diameter from 3 millimeters to some other new diameter as a result of the refraction. So we're going to solve for this D2, and it's convenient to draw this picture of what's happening. So we have a beam with some actual width, and it refracts, changing its angle. So we have some incident angle theta 1, which becomes a theta 2, the refracted angle. But we also have a change in diameter of this beam, which is somewhat interesting. So I drew all the relevant trig that we'll need, and we'll have to just apply it in the correct way. So of course, as a refraction problem, we're going to need to use Snell's law, which simply states that the product of refractive index and the sine of angle is equal on each side of the boundary, where our boundary is from air to glass. So in other words, N1 sine theta 1 equals N2 sine theta 2. So that's really the physics that we need. The rest is going to be geometry. Let's start off. So to start us out, applying Snell's law, we can find, if we know the index of refraction for both media and the incident angle, we can find the refracted angle. By taking Snell's law and inverse sining both sides and just moving some things around using a bit of algebra, we can get to this point where N1, N2, and theta 1 are all known. So we can crunch these numbers. We have 1 over 1.5 sine of 25 degrees. Gives us a numerical result of 16.36 degrees. And this is the refracted angle. Now, consider these two right triangles that I've drawn. We have one right here in the air and one right here in the glass. We're going to use complementary angles and these two right triangles to arrive at a geometric way forward. Namely, the diameters form right angles with the ray direction, and using complementary angles, we can see that the angle between the diameter and the interface is equal to the incident and refracted angles. Since the air-glass interface creates the hypotenuse for both triangles, we use the definition of the cosine to solve for this length in each triangle and set the lengths equal. So let's show that mathematically, what I'm talking about. Namely, D, which is the total length of the interface that's being seen by this beam, you can express that as D1 over cosine theta 1. In a complementary way, we can also express it as D2 over cosine theta 2. And if you're unclear on where this came from, I implore you to just simply look at these two right triangles and apply cosine appropriately. That'll allow you to find D. So this is actually the key. Once we have this result, we don't actually need the value of big D. We just need to equate these two things, D1 over cosine theta 1 and D2 over cosine theta 2. Once we have it, we can solve for little d2, which is the diameter of the beam inside of the glass. Simply d1 cosine theta 2 over cosine theta 1. We know both angles, and we know d1, so we can solve for d2. 3 millimeters times cosine of 16.36 degrees over cosine of 25. Crunch the numbers, and we end up with 3.2 millimeters. So interestingly, this beam, as it passes into a medium of higher index of refraction, actually expands slightly. And the greater the difference, the bigger the expansion. So that's kind of an interesting result.